Thank you for coming. I know this is tough right before lunch. You have low blood sugar, so we'll see how we do here. So my name is Stuart Sierra. I work at Cognitect, and I'm here to talk about a problem that I have. Specifically, I like giving conference talks, but I don't like making slides. So in classic programmer fashion, I decided to make the problem more interesting for myself by making it about 1,000 times harder. So instead of making slides in Keynote or something like that, I decided to make a program that would show the slides for me. So this is a program running in Clojure script in the browser, talking to a web app written in Clojure, talking to a datomic database, all so I can put some slides on the screen and have a big fat cursor to point at things. So I started out doing this, and I'll explain why. But I started doing this with an idea that I wanted to write my slides as data. I wanted to assemble the structure of my slides independent of how they would look on the screen. So I started with a very basic model. A slide is a map. I'm writing this in Clojure, so maps are written in curly brackets, and it has these attributes, an ID and a title. The ID is a keyword. That's the word with the colon in front of it. That is something that I can refer to somewhere else. And I did this because I like to reuse my slides. I like to reuse the same slide in different places. So this slide is actually rendering itself. You could maybe think of it as a quine. And then I also had to put some content in my slides. So now I like to put lots of different things. Sometimes my slides are just images, sometimes they're code, and sometimes they're text. So if I want to represent a slide with some text written in HTML, I'll wrap that in a Clojure list, starting with this symbol, HTML, and then I'll represent HTML tags as Clojure vectors in square brackets. And the tag names are keywords, so this is a head tag and a list tag and some list items, and it would look something like this. So then, I wanted to put code on my slides as well. A lot of my slides have code on them. That tends to be the way I write my presentations. And so I could just embed snippets of Clojure code here in my slides because Clojure code uses the same structure as Clojure data. So I have a list called code, and this includes some code that is the definition for the routes in the web app that's backing this little presentation. But I didn't want to have to copy and paste all of my code into my slides. What I really wanted to do was write this program to show you these slides and then have it somehow display its own source code as slides. So I came up with a way to do that using Clojure's metadata. This caret here means the thing that follows is metadata. It's an annotation about the piece of code that follows. So in my actual source code where I wrote this little app, I have bits of metadata with maps specifying IDs and titles for slides, and then the code that follows that becomes the body of the slide, and it would look something like this. So you don't need to understand this. This is one of the pieces of code that I used to do this. The important part is the reader. Clojure's reader allows me to take all of my source files and parse them into data structures without evaluating them. So I can write a little program like this. This thing basically scans a source file, reads in each of the forms that it contains, each definition or expression or whatever, and then gives them to me as data structures so I can check to see if they have that slide metadata. If they do, I'll grab the source and turn it into a slide. The reader is what makes this possible. I can read a string of Clojure code and get it back as a data structure. In this example, it's a list that represents a piece of code. So next, I wanted to get all my slides in a database so that I could search them and look them up. So I used Datomic, which is a database written in Clojure, to do that. And datomic schema represents attributes as maps of keywords. So my slide ID is an attribute whose type is keyword, the title has a type of string, and so on. So I load all of my slides into this database that I've made, and then I can write queries in Datomic's query language, which is a variant of Datalog represented as Clojure vectors. So I can say find all of the IDs where the ID is some value of this slide ID attribute. So I'm almost done. I almost have a working definition of a slideshow. I've got a bunch of slides, they're all in a database, but I don't have any order for them. So I started thinking, okay, how do I work on a talk? How do I write my presentation? And I tend to think of it in a tree-like structure. I have sections and subsections, and within those, I'll put slides, and I might refer to the same slides several times. So I can write that. I can represent that in Clojure data as lists that are nested inside other lists. So this is my definition of my presentation. It's a slide deck that has a name, it has sections, and those sections have slides inside them. Now this looks like Clojure code, and syntactically it is, but this is not a program. This is not something that ever gets executed or evaluated. It's just a piece of data that I wrote in Clojure syntax to describe what I was trying to build, in this case, a slideshow. Then I can use another feature of Clojure, a fairly new feature called Clojure Spec, to interpret that data structure. This is, Spec is a new library, it's an alpha feature of Clojure that lets you define shapes of data and validate what things they should contain. So I can define, for example, my deck starts with a symbol, deck, then an ID, and then some number of nodes, which are either sections or slide IDs. The details aren't important, but what this does is that it means I can take this thing that I wrote in a format that's very convenient for me to edit and transform it into a more verbose form that's much more convenient to work with in a program. So I can recover some of the implicit structure in this list format that I was defining. So after all that, all I had to do was write a little bit of Clojure script to render these slides as DOM elements in a browser using React and a bunch of other JavaScript, and the result is I have a slideshow. Thank you. So this was the first yak that I shaved in the process of preparing this talk. But the thing is, and the reason I wanted to do this, is that I don't think I could have done this in any other language. The fact that I could represent the actual code of my program, whether it was being compiled for the JVM or for JavaScript in the browser, same code structure, and use that same structure as the data model of my application. So the components of Clojure code and the maps that I was making my slides out of and the data I put in my database all share the same structure. And I could even adapt that structure into making HTML and CSS and the other things I needed to put it on the screen. I'm not sure how I could have done that, especially if I didn't have a reader, something that could read in a piece of source code and then give me a data structure that I can work with. But I still haven't defined this term, homoiconicity. Now there's a sort of a trope that people say if you're doing a Clojure talk, you have to start with a dictionary definition. So I looked in the dictionary for homoiconicity, and it wasn't there. Okay, so no luck there. So let's search on the internet, and of course there's Wikipedia, but who looks at Wikipedia anymore? When you look for this term, you find a lot of references to this thing, the C2 wiki, or the wiki web. This is the original wiki. Before Wikipedia, before any of that stuff, this was the first, as far as we know, the first wiki on the internet. So it was just known as the wiki. And it's been around since 1995. It's been in continuous operation all that time. And it was originally developed and used by people in the software patterns and some of the early extreme programming communities to document their ideas and practices. So it's kind of a fascinating history of some of these software development ideas as they were being developed. Unfortunately, if you go to the wiki page for the definition of homoiconicity, you see this. Turns out, after 20 years of continuous operation, the maintainers of the web decided to rewrite the application in modern JavaScript as a single-page application with a distributed database back behind it. As a result, a lot of the pages look like this. There are a variety of reasons for that. But a lot of the pages that I wanted to look at for the history and people discussing this term were not there. So this started the second yak shave that I encountered preparing this talk. There aren't any public archives of this wiki that I could find. It's not on the Internet Archive, except in one file that somebody uploaded in 2015 that contains a complete copy of the web as it existed at that time, compressed in a text format called wark, which is basically a log of a bunch of HTTP requests. So you can see they're requesting a page, then there's some metadata, and then there's the raw response that they got, including all the chunking. So this was the only format I could find in which I could actually browse the web. So of course I had to write an application to let me view it. There are other tools for working with this format, but none of them were really suitable for just working with one small archive. They were all bigger, more complicated projects. So I wrote in Clojure again a very hackish server that would take an HTTP request on a socket and parse it with a regular expression to try to figure out what page you were looking for, and then jump to that point in this compressed archive and return the raw bytes from the archive exactly as they were. This took me about a day to do. Also, I could click this and actually see, running locally, my own archived copy of the web, complete with all of the original encoding errors and other problems it had at the time. So this is interesting. There are a lot of discussions on this site. It's kind of like a mailing list crossed with a chat room, crossed with, well, a wiki, I guess. And people spent a lot of time on various computer science and programming terms, trying to define what they meant and really come up with strong definitions. So this is the pretty typical definition that they give on that page, that you have the same representation of code and data, similar to what I was talking about with my slides. But they try to get a little more precise than that. So there are some debates, they say, and this is an understatement. There are probably several thousand words of arguments on the web about what this term actually means. And so I read them all so that you don't have to. And there are a few things that they can rule out. For example, simply having reflection, as many languages do, is not enough. Simply being able to bootstrap a language in itself is not sufficient. None of these things alone would imply that your programming language has this property of homoiconicity. So in an attempt to come up with a more rigorous definition, someone set a challenge. They said if you can do these things, then your language is probably homoiconic. And this is expressed in Common Lisp, but the challenge was define a variable, a, with a block of code. So the value of a is now this piece of Common Lisp code to set the value of another variable, b. Then evaluate a and observe the effect. So we've evaluated a piece of code, and we can see it did have an effect on the environment. Next, we have to modify that piece of code. Now this car, coulda, and whatever nonsense, this is just Lisp fashion for deconstructing a list and going into a specific point of it. Basically, this means go to the third element, this number 15, and replace it with the number 37. So then we can look at our code again. This is now our A, our piece of code, evaluate it, and then look at B, and the value of B is now 37. So this is very clearly a demonstration that code in the language and the data structures in the language are the same thing. We can manipulate them, we can evaluate them, and they become part of the program. Another example that people commonly cite, and one of the examples that they used here was TCL, or Tickle. This was a scripting language popular with Unix systems. And you can do something very similar. You can say set a variable to this block of code here, evaluate it, look at the value of b, see that it's 15, and then replace something with 37, and then evaluate a. But here it's actually evaluating a inside an if statement. And so the point is, in Tickle, you don't even need to say eval. If you use a variable in a place where it would be valid to have code, you can actually just treat it like a piece of code and it will work. So the assumption is that in Tickle, these lists in the curly brackets and strings are what make up the structure of your code. But there's something a little bit unsatisfying about this definition, because if you have a language with eval of any kind, you can probably come up with a way to make this example work. And so someone demonstrated that by doing it in Java. They said, okay, all you've said is that we have to, set a variable and make some changes to it. So I can write essentially an interpreter in several hundred lines of Java, and I can make it do the same thing. I can say, create a variable, and then print its value, and then modify it, and then print the value again, and it will do the same thing. So therefore, Java must be homoiconic, right? Well, no, they shut that down pretty quickly. You haven't done eval just because you've made an interpreter in your language. It doesn't mean that it's homoiconic. And they have this great burn to go on to say that you didn't even do that. But the question is why? And people spent, this is where they really had the longest argument, was on this page, about why doesn't this count? So it was very hard to come up with a definitive answer that people would agree with. What it seemed like people were sort of heading towards, and what another page on the WikiWeb eventually said, was that this is a subjective classification and there are degrees. So we could say that some languages like Lisp and Tickle are strongly homoiconic because it's very clear that you can use code and data the same. And then it goes down through various languages until you get to Java and C and other curly brace languages at the bottom. But this seems also sort of unsatisfying, because if it's just a continuum, then how do you really decide where something goes? It's just a feeling, it's a vague idea. So they didn't come up with an answer, as far as I could tell. They had a lot of interesting discussions. The one thing people do agree on, it seems, is the actual origin of the term. So the word homoiconic was coined in a paper in 1965 by these two people, Moores and Deutsch, who were creating TRAC, which was a language and a system for what they called a reactive typewriter, which today we would probably recognize as a text editor, particularly a programmable text editor. But they were doing this on a PDP-1, which had, I think, a few thousand words of memory. It had I/O via paper tape and a teletype. So they were trying to build a sophisticated programmable text editor on a machine that didn't have a screen. Full screen editors would not become common until the mid-70s. So this was a pretty challenging thing that they set out to do. And they developed a very interesting system for doing it. So TRAC was a programming language in which literal strings represented themselves, because it was designed to be embedded in a document that you were typing. So you could be typing a document and then you'd start typing commands in this language TRAC, and they'd become part of your document. So hello world in TRAC is just the text hello world. For another example, I found some old documentation manuals for this thing, and this is an example of the Fibonacci function in TRAC. Maybe not the most intuitive syntax, right, when you first look at it. But again, because I did this, you don't have to, I actually looked at this manual and figured out what these things mean. So hash paren is kind of the escape character that gets us out of verbatim text mode into programming mode. And then all of the other characters, all of the commands have these very short mnemonics. Again, you know, they're typing this on a teletype, so every character counts. So this S means that we're storing something in memory. Fibo is the name of the thing we're storing. This paren here is a block. And then the first statement in the function, EI, stands for an equality test on integers. The brackets mean the argument, so if the first argument is equal to 1, then this function evaluates to 0, because that's the first element of Fibonacci. Otherwise, go to this block, test if the first argument is equal to 2. If it is, return 1. Otherwise, well, what is this? Okay, all of the arithmetic commands start with A. So AA means add, AS means subtract. So we're going to subtract 1 from the first argument, subtract 2 from the first argument, and use those to invoke Fibo again. RI means recall the value of this symbol Fibo and then interpret it. So this is a recursive call to the same function we're defining on the argument -1, the argument -2. Take the two of those, add them together, you get the nth element of Fibonacci. So if you thought that was difficult, this is indentation in a language called Mint. So Mint is the native language of an editor called Freemax, which was a version of Emacs written for FreeDOS, an open source version of the DOS operating system. And so Freemax borrowed a lot from TRAC, but they knew that Moores, in particular, had trademarked the name TRAC, and he was very litigious. He actually pursued a number of lawsuits against people for trying to do things with TRAC without his permission. So they named their language Mint is not TRAC, to make sure it was clear that they were not copying him. But it does look very similar. So this is the procedure in the Freemax distribution, which you can still find, to indent a block of C code. And it's a little more modern. It's got actual plus signs and multiplication signs, but it's still a fairly terse language with these funny characters. There is, incidentally, a version of Freemax that someone ported to C++, and you can supposedly run this on a modern Unix system. I tried. Unfortunately, I couldn't get it to compile. But if someone out there really wants to write in this language, you have an option there. Okay, so back to TRAC. TRAC had some very interesting ideas, some of which were really quite unusual. The way TRAC operated was as an interpreter. TRAC was a program they would load into the PDP-1, and then it would load your document and interpret the characters in your document, including the control and command characters. So they thought this was a really essential property, that the text that you type in your program is the same as the text that the interpreter operates on. In fact, it is literally the same bytes. You write your program in ASCII characters. Those ASCII characters get stored at a location in memory. When you invoke one of those functions, this interpreter will go to that position in memory and start reading it one character at a time and evaluating it as it goes. So there's no other representation of the code anywhere. There are no compiled forms, there's no bytecode, no intermediate parse tree or any other kind of structure other than the literal text of the program itself. And this, they decided, was what actually made their language TRAC homoiconic, because the procedures that it runs and the text in memory have exactly the same representation. So homoiconic, they mean homo for the same, icon meaning representation. So this is actually quite a strict definition. This says that everything has to be exactly the same inside and outside of the computer. Now, they put an interesting little footnote on this statement where they defined this term. They say, following suggestion of McCulloch based on terminology due to Peirce. So I started trying to track these down. Now, they misspelled his name, but as near as I can tell, McCulloch is Warren Sturgis McCulloch with a CH, who was in Cambridge at the time, although he died a few years later. And he was a mathematician and computer scientist, had done a lot of interesting work on what we would now call neural networks, including some of the earliest papers demonstrating that a neural network could perform all the same computations as a Turing machine. So he was probably friends with these people. They were all around MIT and Cambridge, and they all knew each other. So he suggested the term homoiconic, and I guess he's the reason I'm here today. And he said, referring to terminology due to Peirce, C.S. Peirce. So who was that? Well, that was an American mathematician and philosopher named Charles Sanders Peirce. He was quite a remarkable mathematician, although not well known in his day. He did some really innovative things, including suggesting, possibly for the first time, that you could run Boolean calculations on electrical switches, decades before anyone had tried building an actual electrical circuit to do that. Unfortunately, despite his innovation, I still can't put an image and a bulleted list on the same page in HTML and not have them overlap. So some problems just can't be solved. Later in his life, Peirce became a philosopher, and he was actually better known in philosophy. He worked on a number of different fields. The one that is relevant here is this thing called semiotics. So I tried to read through a few summaries and descriptions of what this means, and I encounter sentences like this. And so I just want to say, if you've ever read documentation and you thought, wow, this is really poorly written, it's really dense and really abstract, and I have no idea what they're talking about and who even writes this stuff, my only suggestion is, go read some philosophy. You'll feel better. So I won't pretend to understand what this means. What I can tell from the summaries that I dragged myself through is that semiotics is all about the relationships between things and their representations. So sort of the idea is that when you perceive a word or a symbol like defun, that has a relationship with the idea that's created in your mind. So you see a word, you think of the definition, and then there is some other relationship between that definition and the actual thing that you're talking about, which may be a real physical object, or it may be an abstract concept, like defining a function. So you can pretty easily see how this might be relevant for computer programming. I mean, this is essentially what we do all day. We define words that have abstract meanings, and then we think about them, and we are really bad at drawing. Okay. So I'm still on the TRAC paper. TRAC references a number of other systems that inspired it, including Comet, which was another early text editing system, and Lisp. So the TRAC folks were very familiar with Lisp. In fact, Peter Deutsch had written the implementation of Lisp for the PDP-1. So these guys definitely knew their Lisp. Now Lisp, of course, had only been around for a few years at this point. It was invented by John McCarthy in the late 50s. And the original idea, McCarthy's original idea, was not to make a programming language. McCarthy wanted to make a notation for describing programming, maybe something akin to the lambda calculus or a Turing machine, but a little more easily defined and a little more easy to work with. So he came up with this language called Lisp, in which you could define a procedure Eval, which described how to evaluate the language in terms of itself. And this is where the term metacircular evaluator comes from. You can actually write the implementation of Lisp in itself in a very small amount of code. This is the whole thing. And this syntax, by the way, this was McCarthy's original syntax called M expressions with functions and their arguments in square brackets. But you can see this is fairly straightforward. You don't need to know the details, but these are a bunch of symbols, and it's testing to see if the thing we're looking at is one of those symbols, and it knows how to evaluate each one. So you can imagine this is a little interpreter that is stepping through a list of symbols, figuring out how to evaluate each one, and then it has some special rules for local variables and lambdas and things like that. Now this was the M expression syntax. What people probably are more familiar with when you think of Lisp is the S expression syntax. So this is a version of that same eval procedure written in Common Lisp as an example by Paul Graham. But you can see it's the same basic structure. A bunch of equality tests and rules to recursively invoke eval to deal with different kinds of symbols. So the TRAC authors were aware of this. In fact, they were fans of Lisp. But they thought, you know, Lisp didn't really go far enough. They thought this was a flaw in Lisp, that you had to implement it in machine code. So originally Lisp was not supposed to be a programming language until one of McCarthy's students figured out, hey, that eval procedure, I can code that in machine code, and then we can actually have an executable version of this language. So they did that, and that led to the first Lisp implementations as programming languages, which again, Deutsch had worked on for the PDP-1. But he really thought, you know, this feels like cheating. We had to leave the language, leave that cool, abstract metacircular evaluator behind and just write some messy machine code in order to get it to work. Now, their language, TRAC, did not have this property. It was strictly an interpreter, which of course they must have written in machine code. But then once you were in that interpreted language, you couldn't escape it. It was all of the functions you could define in that language were within the language. There was no way to drop down to a lower level and write something in machine code. But here we have the people who coined the term homoiconic deciding that Lisp really wasn't homoiconic. It was close, but it didn't quite get there. And that's because they thought these M expressions were an unnecessary layer, and the S expression language, if you leave out all of the machine code, maybe we'll let you say that Lisp is homoiconic. They also had this to say, and this is in the paper as their reference to Lisp. They said, really, they couldn't understand it. They'd implemented it, but only people who had the necessary mystique could understand it, and they were just making a simple text editor, and their humble users wouldn't be able to grasp the subtleties of Lisp from its documentation. This might be the earliest recorded complaint about Lisp documentation. So there they were, 1965. So a few years after this, after TRAC had been out there, Alan Kay, who would later go on to make Smalltalk and a lot of the concepts that we now know as object-oriented programming, he wrote his PhD thesis in 1969 about a language called Flex. Now, Flex, the language, never really caught on. Bits of it made it into Smalltalk. But he was interested in building interactive computer systems, which is, of course, where Smalltalk came from. And so Flex was an early attempt at doing that. It was supposed to be an extendable, flexible language. And he referenced both Lisp and TRAC as inspirations. And he said they're both homoiconic because their internal and external representations are essentially the same. So I'm not sure if he ever discussed this with the TRAC authors, but maybe they could have had a fun argument over a few beers about this. In any case, Alan Kay had his own opinions about these languages. He thought they were a bit hard to read. And I got to say, so this might be the oldest recorded complaint about Lisp syntax and having too many parentheses. And I got to say, if you're going to criticize a language syntax, this is the way to do it. I mean, this has style. He's referencing ancient cuneiform. Now, because I was trying to be thorough as I prepared this talk, I actually found a copy of this letter. And that is what it looks like. Unfortunately, I couldn't get this to compile, so I don't know if it's actually equivalent to Lisp, but we'll have to take Alan Kay's word for it. So all this, I still don't have my definition. So I did what any programmer in 2017 would do. I posted a question on Twitter. And I asked this question just in general and asked, what does this mean? And people gave me all sorts of interesting answers. Some of them were fairly traditional, code and data, same representation. Some were focused on manipulating the code as data. I thought that was really the important property. And some people had more philosophical answers. They said just everything has to be balanced. Life, the universe, everything. So I thought that was an interesting answer. I think my favorite, though, was this. In the chain of representations between desire and effect, there is a point, one point, at which both sides are thinking about the same shape. And I like this because it sort of implicitly admits that when you're dealing with programming, there will always be many representations. Programs may be represented as ASCII characters. Those ASCII characters are represented as bytes. Bytes are bits. Bits are represented as electrons or something. So there are always many representations you have to think about. The important property for a homoiconic language is that somewhere you have the same structure, whether you are reading the language or writing the language. So given this, I came up with my own definition, and this is very ad hoc and based on my own personal sort of prejudices. And you're free to argue with it. I'm sure some of you will. But I said in order to be homoiconic, a language has to have literal data structures. This, for me, is the key property. It has to have something where I can write some syntax and have that be a data structure. So in Lisp-like languages, I write lists in parentheses. In TRAC, you write the hash curly, and that becomes a function in the representation of the language. And then you have to use those data structures to write the code. So whatever, this is the key feature. Whatever the structure of your language is, it has to be represented using the literal data structures. And very few languages actually have that property. Now, just to sort of make this more precise and to cut short any arguments, I said strings and byte arrays don't count. You can write an interpreter for strings or bytes, or say that everything is bytes eventually. So it doesn't count if you've just evaluated some strings in your language. But I somehow have to fit TRAC and tickle into the definition, and they basically operate on strings. So I'm just going to grandfather them in. I don't know any other way to resolve this in my mind. So that's my definition. Lots of languages have variations of this property. Lisp is written with lists. Prolog is written with terms and clauses. XSLT is an interesting example. It's actually written in XML, and it manipulates XML. So you could, in theory, you could write an XSLT program that manipulates another XSLT program. So why do I care? What's interesting about this? For me, the most interesting feature is actually just being able to see what's going on in my program. I can grab some value while my program is executing with a logger or a debugger or something like that, and then just print it out and look at it. If I have a map in Clojure, I can just look at it in my Clojure REPL. And then I might take a version of that map and just copy and paste it into another piece of code and use it as input for a test. So the fact that I can very easily sort of copy and move data around in between my running program and the text of the program I'm working on is a really powerful feature. Another cool thing, and I think this is sort of an underappreciated feature of homoiconic languages, is this ability to start expressing a concept in the language without actually having to put it in code. So when I was making my slideshow, I knew that I was going to arrange my slides in some kind of list or tree-like structure. But I didn't really have an idea. I mean, I had a rough idea, but I didn't know exactly how I was going to implement that in code. And if I'd tried to write code for these things, I might have ended up with something a lot more rigid and a lot more brittle than what I actually wrote. So simply being able to write data that can become data in the language that I'm working with is a really powerful feature. Now, the thing that most people will sort of jump to when they're talking about homoiconicity and talking about the advantages that it brings is macros. And macros are cool, no doubt. They allow you to extend the language with new concepts, in particular, new control flow and evaluation constructs. So one example of this is the with open macro in Clojure, where you can write with open in your program, and that will expand out to a bunch of nested try finally close blocks without you having to repeat that kind of messy structure over and over in your programs. Now, this is a very useful property. It definitely lets you make things more abstract, more succinct, more precise. In fact, most of the control flow and evaluation constructs in Clojure itself are implemented as macros. So when you're writing macros, you're essentially operating at the level of language definition. And that is a really powerful feature for metaprogramming and all kinds of things. However, I do think macros are limited in the fact that they run only once. Macros in a program run once when your program is being compiled. After that, they're gone. And you don't get a chance to look at that structure again. So unlike my data, where I define my slides, I can read that while my program is running, interpret it, and look at it again and manipulate it. I can't do that with macros. So a common mistake I think people make when they first come to a Lisp-like language, such as Common Lisp or Scheme or Clojure, is they try to do too much with macros. And that can actually get you into a lot of confusion and a lot of trouble. So finally, I built my slideshow, I built my presentation, I did all my research. What really stood out for me, again, is that I don't think I could have done this in any other language, certainly not in any language that didn't share these properties. I can manipulate data, the same data that I'm using to write my code, which means the code becomes something more. It's also data. I can very trivially write tools that will examine that data. I could search it, index it, build other tools around it. Things that would be maybe possible in other languages, but much more complicated to do because you have the added burden of dealing with syntax for which there is no data structure representation. So that is everything I have to say. Again, I work at Cognitect. I think our booth is closed, but I'll be hanging out in the lobby if you want to argue with me about any of my definitions. You can also find me on the internet, of course. Thank you.